Hey there, welcome to Axiom. So, a lot of you have been asking me to cover transmission media in computer networks, and I finally got around to making this video. Trust me, once you understand this, everything else in this chapter clicks. Let me explain. When we think of digital data, we tend to picture abstract ones and zeros floating in a cloud, but data does not exist in a vacuum. It is physical energy moving through physical space. That energy has to travel through an environment. Sometimes it moves through bounded media contained within copper wire or glass fiber.
Other times it moves through unbounded media, radiating across the open air or through a vacuum in the OSI model. This is the physical layer. This is the exact point where software instructions are converted into electrical voltages or optical waveforms. But no transmission medium is perfect. Every physical path needily resists the transfer of energy. This diagram shows what happens during transmission. A perfectly symmetrical wave leaves the transmitter, but as it moves across the network link, it is flattened, spiked, and deformed by the journey. This is the absolute rule of networking. What is sent is never exactly what is received. The signal always degrades. To build reliable networks, engineers must mathematically deconstruct and neutralize the three specific physical forces destroying the data: attenuation, distortion, and noise. The first force is attenuation. This is the literal loss of a signal's energy and amplitude as it travels over a distance. As the electromagnetic signal moves, it has to expend its own energy to overcome the inherent resistance of the copper, glass, or air it is passing through. This chart shows the life cycle of a wave losing power over distance. Looking at the space between point 1 and point 2, the wave visibly shrinks in height. The energy is bleeding out into the transmission medium. Engineers precisely measure this loss using the decibel. It is a logarithmic unit comparing the original input signal's power against the resulting output signal. To compensate, physical networks use an inline hardware amplifier. Placed between point 2 and point 3, it injects fresh energy, restoring the wave's amplitude. Because the decibel is a logarithmic unit, engineers can easily measure cascading cable links. Instead of performing complex multiplication for every segment, they simply add or subtract the decibel values. This diagram shows how that calculation works in practice. If a specific cable is rated at a loss of negative zero point 0.3 decibels per kilometer, a 5-kilometer run results in a simple total loss of negative 1.5 decibels. Attenuation dictates the absolute maximum physical distance a specific cable can be run before an amplifier is strictly required to prevent total signal death. While attenuation only changes the wave size, the second force, distortion, warps the signal's actual shape. Real world network data is rarely transmitted as a single simple wave. It is sent as a composite signal, built from multiple distinct frequencies combined together. This creates a physical dilemma. Each independent frequency component travels through a given medium at its own unique physical speed. In the at the center box, three distinct subwaves start perfectly aligned and in phase. Traveling at varying speeds, they arrived with different delays. On the right, they are horizontally misaligned and out of phase. Recombined, the resulting composite wave is geometrically mutated. Distortion is a timing failure. Without phase coherence, the hardware cannot decode bits regardless of remaining raw energy. The third and most chaotic destructive force is noise. This is the addition of unwanted external electromagnetic energy into the transmission channel. The baseline is a microscopic, unavoidable source called thermal noise. This is caused by the random erratic movement of electrons inside the wire itself. Then there are localized external sources. Induced noise occurs when nearby motors or appliances act as accidental transmitting antennas. Crosstalk happens when signals bleed between adjacent wires inside the exact same cable. The most severe is impulse noise. These are sudden massive spikes in energy caused by unpredictable events like power line surges or atmospheric lightning. In the middle section, an erratic jagged noise wave drops into the transmission path. The clean signal and noise merge at the receiving end. That massive noise spike is permanently baked into the original wave's pattern. Because background noise is a permanent physical reality, engineers must measure a system's raw viability using a metric called the signal to noise ratio or SNR. This chart shows that mathematical ratio, comparing the power of the intended data signal against the power of the background noise measured in decibels. A high SNR means the data safely overpowers the environment. A low SNR means the intended message is drowning in physical static. We can observe the total life cycle of signal failure by forcing an original wave to endure all pre-phenomena simultaneously. This diagram shows a perfect wave entering the medium. First, attenuation applies and it shrinks in height. Next, distortion takes hold and its edges warp and shift out of phase. Finally, noise is injected, leaving it violently jagged and unrecognizable. Defending against this combined degradation is exactly why different network tasks demand drastically different physical media. Unshielded twisted pair copper is cheap to install, but it is highly vulnerable to crosstalk. Coaxial cables solve this by encasing the core in a heavy physical metal mesh to block external electromagnetic noise. Unguided radio waves offer different trade offs. They can penetrate building walls, but they suffer from massive atmospheric noise and severe signal attenuation over distance. Fiber optics sidestep electrical noise entirely by using light refraction inside glass, yet, even they are bound by the rules of optical attenuation over vast geographic spans. The physical layer is a constant mathematical war against entropy. Only by calculating energy loss, phase shifts, and external interference can engineers guarantee that what is sent is ultimately received, and there you have it. Transmission media simplified. Remember, understanding the basics is key to cracking exams. Hit like if this helped, subscribe to Axiom for daily lectures, and comment below with any doubts. I read every single comment. See you soon.